So let us discuss this problem. Let x1, x2, xn be independently distributed random variables with moment generating function xi be mxit. Find the moment generating function of y is equal to summation of I is equal to 1 to n xi. So let x1, x2, xn be independent random variables with moment generating function of xi is mxit for I is equal to 1 to n. It is a general case. In a particular case we can discuss where some of the mxit value. Find the, y is equal to summation of xi. We have to find the moment generating function of n. Suppose these are all known. So the moment generating function of y is, so define what is the definition, myt, this is nothing but expected values of e to the power of ty, myt expected values of e to the power of ty, which is equal to expected values of e to the power of t summation of xi. So because ty is nothing but summation of xi, so basically if we explicitly write that expected values of e to the power of t x1 plus x2 plus xn, so then if you simplify these things, this is expected values of e to the power of tx1 plus tx2 dot dot plus txn. So this is expected values of e to the power of tx1, expected values of e to the power of tx2, expected values of e to the power of txn. So now this function can be written as mx1 of, so what is this? So these things expected value of tx1, it is nothing but moment generating function of x1. Similarly, it is nothing but a moment generating function of x2. Like this moment generating function of xn. Because all these moment generating function of it is known, so this is can be represented as product of I is equal to 1 to n mxi of t. So if you know the moment generating function of the independent random variable mxit, then just you multiply those moment generating function to find the moment generating function of the sum of this random variable. This is the one property of the moment generating functions. So hopefully you have understood it. So next we will discuss this example. Let x1, x2, xn be a set of independent random variables with xi has Poisson lambda. So that we just discussed earlier, that if you have n number of random variables with Poisson lambda I and you want to find the distribution of y is equal to summation of xi, how we can find that? So first what we will do for finding distribution of y, so first we need to know the moment generating function of the Poisson with parameter lambda. So in general case, so let us find that. So let x be a Poisson random variable with parameter lambda. This is should be greater than 0. The moment, so first of all the probability mass function let us write down, because we have to find the moment generating function, we need that. For probability mass function we have to find the probability mass function of x is given by, so this is px of, suppose let us for simplicity let us write only k. So px k, this because these are all integer values, so e to the power of minus lambda to the power k by k factorial, whenever k can take 0, 1, 2 like this and 0 otherwise. Then we can find the moment generating function from the definition. The moment generating function of x is given by mxt is equal to expected values of e to the power of tx. So by definition, because it is a discrete random variable, summation of k is 0 to infinity e to the power of t into k, x taking the values k into px of k. So then summation of k is 0 to infinity e to the power of tk, then pxk here, this is e to the power of minus lambda, lambda to the power k by k factorial, whenever k is 0, 1, 2 like this. 1 minute, sorry, why I am writing this. Basically, this is I have written here. So here k is equal to 0 to infinity. This is the probability mass function. Now we have to find out the solution. So we have to find the simplified form. So how we can do that? Because lambda e to the power of lambda, it is a constant, e to the power of minus lambda, it is no k involved, k equal to 0 to infinity. Now we can lambda e to the power of t, we can write whole to the power k by k factorial. So this is minus lambda e to the power minus lambda. So this is nothing but 1 plus lambda e to the power of lambda by 1 factorial plus lambda e to the power of lambda t e to the power of lambda e to the power of t, lambda e to the power of t square by 2 factorial like this. So this is an infinite series. So we know that this expansion looks like e to the power x 1 plus x square by 2 factorial plus x cube by 3 factorial like this. So that's why this is nothing but e to the power of minus lambda, this converges to e to the power of this x here, lambda e to the power of t. So hence we can write e to the power of lambda e to the power of t minus 1. So it exists for any t in a real number. So this is the probability mass homogeneity function of a Poisson random variable with parameter lambda. Hence, so you can remember that. So suppose this is the form of this homogeneity function of a Poisson random variable. Suppose one random variable, suppose w, it has homogeneity function mwt. Suppose let w be a random variable with homogeneity function. Suppose homogeneity function, we don't know what is the distribution, but we know the homogeneity function. With homogeneity function mwt is suppose e to the power of 2 e to the power of t minus 1. So then you see that you compare with these things, it looks like very similar, but this lambda is just changed here 2. Hence by comparing here we can say that, which implies w is, because by the uniqueness theorem of the homogeneity function, so it cannot have different. So w, if w is a Poisson random variable with parameter 2, lambda is 2, then this homogeneity function looks like this. So there cannot have any other distribution having the homogeneity function, because if two different random variable having same homogeneity function, then they must have same. So by this uniqueness theorem we can say that w must have Poisson distribution with parameter 2. So that is the usefulness of the for identify a distribution through the homogeneity function. Now here we will now see this problem. So we have to here find the distribution of y. Now first of all, x1, x2, xn are set of independent random variable with each xi is Poisson lambda. So let us go through it. So let x1, x2, xn be independent random variables, independent random actually having with xi has Poisson distribution with parameter lambda I for I is equal to 1 to n. So here lambda I are greater than 0. So lambda I should be greater than 0. So here we can write lambda I, all lambda I should be greater than 0 for I is equal to 1 to n. So they are independent random variables. Now hence we know that what will be the homogeneity function of xi, because we have just computed just now, because parameter lambda I we replace lambda by lambda I here. The homogeneity, hence the homogeneity function of x is given by mxt expected values of. So here actually directly we write that, we will not compute this. So mxt, so homogeneity function of xi here, for the homogeneity function of xi is given by mxi of t. So mxi of t parameter Poisson is parameter lambda I. So it will be e to the power of lambda I e to the power of t minus 1. So now we will use this theorem. Hence the moment genetic function of y is equal to summation of xi, because they are independent, xi I is equal to 1 to n is given by, so m of y t. So now these things we have already done. So here in this theorem, here we can see that whenever x1, x2, xn be independent random variable moment genetic function mxit in general case, so my2 will be nothing but product of their individual moment genetic functions. So this is nothing but product I is equal to 1 to n mxi of t. So mxi of t it is here. So this is product I is equal to 1 to n e to the power of lambda I e to the power of t minus 1. So this product, I think you understand this. So several times we have used those kind of notations. So or explicitly we can write also. So now this is nothing but just e to the power of lambda 1 e to the power of t minus 1 into e to the power of lambda 2 e to the power of t minus 1 e to the power of lambda n e to the power of t minus 1. Just I explicitly write this things. So this is nothing but, if you take this is nothing but summation of these things. So this is lambda 1 e to the power of t minus 1, sorry, e to the power of t minus 1 plus lambda 2 e to the power of t minus 1 plus lambda n e to the power of t minus 1 in the power. So because it is multiplication, power it will be summation. So it will be, so summation of lambda I into e to the power of t minus 1, e to the power of t minus 1 common for, so this is summation of. So this is nothing but e to the power of, we can write some lambda dash e to the power of t minus 1, where lambda dash is nothing but, so lambda 1 summation of lambda 2 plus lambda n. So now you compare with the Poisson distribution. Now we don't know the distribution of y, but it looks like very similar to these things. Now if hence by uniqueness property of this hence by uniqueness property of moment genetic function, y has Poisson distribution with parameter lambda dash is equal to, so this summation of lambda I. So what we found that, see that for x1 is Poisson distribution parameter lambda 1 and x2 is Poisson distribution with parameter lambda 2. We shown that x1 plus x2 has Poisson distribution parameter lambda 1 plus lambda 2, directly finding the probability mass function. Here for general case, like whenever if you consider x1, x2, xn independent random variables and their Poisson distribution, what we found that if x1, x2, xn are independent random variables with each xi has Poisson distribution with parameter lambda I, where lambda I is greater than 0 less than infinity, for I is equal to 1 to n, then y is equal to x1 plus, then y is equal to x1 plus x2 plus xn, it has Poisson distribution with parameter lambda 1 plus lambda 2 plus lambda n. So this is the general things we have proved here using the moment genetic function. So hopefully you have followed it and you understood these things. So next we will discuss some more examples also, how moment genetic function may be useful. Find the distribution of y is equal to summation of xi, again similar type of problems, where x1, x2, xn are independently distributed random variables with xi is normal mu I sigma square for I is equal to 1 to n. So here already we discussed that xi summation of a random variable is again a normal distribution, but here using the homogeneity function we can prove it. So how we can do that? So let us recall that what is the homogeneity function. So let x1, x2, xn be independently distributed random variables with each xi is normal, mean, mu, I, variance, sigma square. So we can consider different sigma I for different I also, but here it is given normal mu I sigma square for I is equal to 1 to n. So recall that if x is normal mu sigma square, the MGF homogeneity function of x is given by, so mxt, this is e to the power of mu t plus half mu square sigma square, half sigma square t square. So sigma square t square by 2, sigma square t square by 2. So let us see that we have just gone through this. Here it is. So this is the whenever x is y is normal mu sigma square, then my2 will be e to the power of t mu plus t square sigma square by 2, t square sigma square t mu plus sigma this is t square sigma t mu plus t square sigma square by 2. So that we have written here. So hence the homogeneity function of xi is mxit, this is equal to, so homogeneity function of xi, just here this mu I it is changed. So e to the power of mu I t plus sigma same for all I, sigma square t square by 2. So this is the homogeneity function of xi. Now we use this result, then the homogeneity function of y is equal to summation of xi is equal to I is equal to 1 to n, because they are independently distributed random variable. We use these previous results. Each homogeneity function of y is given by MYT. So this is expected. So we will write the property, because they are independently distributed random variable. This is I is equal to 1 to n mxi of t. So this is nothing but product that I is equal to 1 to n e to the power of mu I t plus sigma square t square by 2. So because this is product, it will be sum. So see that this is sigma all same. So this will be e to the power of summation of mu I t plus this is sum of n times it is sigma square t square by 2. So please go through this. So how we can sum, because you can write product. So this product is the power, it will be summation of mu I into t. Mu I is the different, but here sum of n times it will be sum of sigma square. So n sigma square t square by 2. So hence this looks like e to the power of summation of mu I t plus, so t square coefficient is n sigma square and then t square by 2. So this is also looks like very same as the this random variable, this homogeneity function, only mu is changed by summation of mu and sigma square changed by n sigma square. Hence from the uniqueness property, hence by the uniqueness property of homogeneity function, y is equal to summation of xi has normal distribution with mean. So mean here from this parameter you can see that summation of mu I, mean summation of mu I, and variance, see that variance sigma square is replaced here by n sigma square. So this is variance n sigma square. That means yi has that means yi has normal summation of mu I and variance n sigma square. So this is just using the homogeneity function we can conclude that. So that sum of the normal distribution again the normal distribution, and this mean will be summation of the mu, because they are independently distributed random variable. That's why this will be summation of mu I, and variance will be n sigma square. So hopefully you have understood it, and then we'll discuss so some new topic. So first of all, what we found that all of these cases homogeneity function exist, but we discussed that this homogeneity function may or may not exist. So let us discuss some example where homogeneity function may not be may not exist. So that we will discuss one example. Let us consider this example, this discrete random variable x with probability mass function given by this. So let us consider the discrete random variable x with the probability mass function given by Pxx is equal to 6 by pi square x square whenever x is 0, 1, 2 like this. This is 0 otherwise. So this is the probability mass function. Now this random variable, so how this is we have already earlier we discussed that this is this is cannot be 0, then it is undefined. X can be, this is from 1 to like this, 1 to this. Now whether it is a probability mass function, because this is always greater than equal to 0, and not only that, if you take the sum of all these things, all the possible value 1 to infinity, this is 6 by pi square summation x is equal to 1 to infinity 1 by x square. So this sum is, you know that this is, you can, so this is pi square, this is a convergence series and converges to this value, so this is equal to 1. So now if homogeneity function exists, so then it can be expanded as a they are infinite series of the moments. So now if you if the moment does not exist, so then homogeneity function cannot exist. So then you can see that what is the homogeneity function. So homogeneity function expected value with the power of Tx. So this is equal to summation of x is equal to 1 to infinity. So e to the power of Tx, then probability that x is equal to x. So which is equal to summation of x is equal to 1 to infinity e to the power of Tx, Pxx is nothing but 6 by pi square x square. So summation of x is equal to 1 to infinity 6 by pi square, it can be outside 6 by pi square, and then summation x is equal to 1 by e to the power of t square e to the power of tx by x square. So these things, how we can show that this is, so it can be divergent, because see 1 plus e to the power of tx contain higher term 1 plus tx plus tx square, all are positive term. Now let us, so this sum will be actually greater than equal to, so like you can show that this sum, this is summation of x is equal to 1 to infinity e to the power of tx by x square. So this is greater than equal to the summation of x is equal to 1 to infinity. So t of, suppose if you consider any, suppose x by x square, because this contain for t any positive value, suppose if you consider t in a positive value, tx can be represented as 1 plus tx square by 2 factorial, all these things. So other term will be positive, so we are not considering only this term, so that's why this will be greater than, basically strictly greater than, and this sum will be also, this is nothing but sum, if t is positive or so then this term will be t is non-zero value, sum x equal to 1 to infinity 1 by x, it is a divergent series. So this is not convergent. So this is actually goes to infinitive. Actually this sum is not, it is a divergent series, does not converge in a finite value. So now that's why it is not. So now in other way we can discuss that what is the moments. So basically we consider this first order moments, suppose mu1 dash. So this is by definition summation of x is equal to 1 to infinity x into px of x. So this is summation of x is equal to 1 to infinity x into px of x is equal to px of x is 6 by pi square, 6 by pi square x square. So 6 by pi square is a constant, 6 by pi square summation of x is equal to 1 to infinity x 1 by x. So this is a divergent series, it does not exist finitely. So that's why the mu1 dash does not exist, and in general mu1 dash does not exist for any r for r is equal to 1 to none of the first order, second order, third order moments does not exist. So in a finite value, hence the moment genetic function does not exist. So the moment genetic function of x does not exist. So that is one example that. So in that case we don't have the moment genetic function. So there may be some other example also, like moment genetic function does not exist. So now whenever moment genetic function does not exist, if you want to get some similar property, so we actually then we there is some different definition. So another function, it is known as characteristic function. So characteristic function is defined by the characteristic function of a random variable x is defined by, so it is very similar to the moment genetic function, but little modification is there, like it is denoted as psi x. So moment genetic function we define phi x, psi xt, it is e to the power of, so it was earlier it was tx, just it is multiplied by j. So where j is the complex number root over of -1. So then what is the benefit here? So expected value to the power jtx, suppose if it is a discrete, so for example let us consider it is a continuous. So like if it is a discrete, then this definition is nothing but summation of all xk e to the power of jtxk, probability x is xk whenever x is a discrete random variable, is a discrete random variable, and this is minus infinity to plus infinity e to the power of jtx fxx dx whenever x is a continuous random variable. So now why it is what is the benefit, like with if we add this instead of t, if we add a -1 it to the power of -1, because if you take, because moment genetic function may not exist for all the random variable, what about psi xt? If you take this psi xt, suppose if you consider this continuous random variable, discrete case will be very similar. So if you consider psi xt, mod of psi xt, it is nothing but mod of minus infinity absolute values of this jtx fxx dx, which is less than equal to minus infinity to plus infinity. If you take the absolute value inside, so e to the power of jtx fxx, already it is a positive number, always greater than equal to 0, so absolute value will be same as this. So now what is e to the power of jtx? So this is the mod, so mod of a complex number. So e to the power of jtx is nothing but we can write cos tx plus j sin tx. Now what is the e to the power of absolute values of this? So this is the mod of this. So it is equal cos square tx plus sin square tx, root over of that, so root over of this is equal to 1. So cos square tx plus sin square tx is 1, root over of 1, this will be 1. So that's why this is 1. So this value is nothing but minus infinity to plus infinity fxx dx. So because it is a density function, this value will be equal to 1. So mod of this psi xt will be less than equal to 1. So that means this always it will be convergent, so it will not be infinite or minus infinity any value, it will be some finite value, so it always exists. So other properties are very similar. So and also whenever homogeneity function exists, if you replace t by jt, then you will find the characteristics function. So for example, in this case of if x is normal distribution, normal 0 1, sorry, if we consider instead of 0 1 more general case mu sigma square, then you know that homogeneity function is just we computed mu t plus sigma square t square by 2. So then psi xt, if you just replace it t by jt, so then j mu t plus, so e to the power of, it will be e to the power of j mu t plus, so j square t square, so j square is minus 1, so that's why it will be minus of sigma square t square by 2. So this will be the characteristic function for, so this is the characteristic function for characteristic function of x. So that is the that's why we have already discussed homogeneity function in details, and characteristics function, when homogeneity function exists, then just you replace t by jt, then you will find the characteristics function of x, and the other properties, whenever homogeneity function exists, properties will be very similar. So whenever homogeneity function does not exist, then we can utilize characteristic function, we can find the characteristics function, and so that is the one advantage of using the characteristic function. So this is the concept of homogeneity function and some of the numerical examples, their properties, how homogeneity function can be utilized for the finding the unknown distribution, especially for the transformation of random variable, finding the distribution, how homogeneity function used, that also we have discussed. So hopefully you have followed it, you understood it. You have in the references there are many numerical examples. You can go through those numerical examples for homogeneity functions and the transformation of random variables also to get the better clarity. So next we will discuss some other topic. So next we will discuss some important inequality. So we will see that this inequality, it is named as Chebyshev inequality.